Okay. So the most important part, I wanted to say that I've had the opportunity to work with a lot of smart people here exploring holographic complexity this year. I don't have the time to present all of the results, and so today I'm just going to focus on one project which should be coming out next month about trying to understand some issues in complexity in quantum field theory. So where does the talk start? Well, it actually started half an hour ago. So Lenny Susskind brought our attention to two new observables or constructions in ADS-CFT. And so they're related to two different conjectures having to do with complexity. The first I'll call complexity equals volume. Whereas Adam described, I'm looking at the volume of an extremal codimension 1 surface. So it's very much like holographic entanglement entropy, except now what's anchoring the surface is the Cauchy surface on which I'm evaluating the state in my boundary theory. The other version of this story is the so-called complexity equals action, where what I'm doing is I'm evaluating the gravitational action on the Wheeler-DeWitt patch, which you can think of as the domain of dependence of this extremal surface in the bulk here. And by design, both of these observables probe the interior of the black hole, and they continue to evolve to arbitrarily late times. And generally, they're interesting constructions, interesting new observables that we can study in the context of gravity in anti-de Sitter space, and we can try and understand what the properties are and how they behave in different contexts. And as Adam described, they generally satisfy our expectations for complexity, and hence the name for these two conjectures. However, after all of those various explorations, one is still left with a large number of questions. But the key question, what we'd really like to understand is, what are these objects, what are these constructions dual to in the boundary theory? And the idea is that they have something to do with complexity in the boundary CFT, but if we don't really understand what complexity in the boundary CFT is, it seems that it's going to be hard to make progress with these questions here. And so what I'd like to report on today is some tentative steps towards understanding complexity in the context of quantum field theory. So let's start again by, or let me start again by reviewing this idea of complexity, since it is a new idea for many of the people in the room. And so the question, that we're asking is basically, how hard is it to prepare a given state? And so we're going to use a model that often goes by the name the quantum circuit model. And so we start with a simple reference state. If we're working with qubits, they might be all spins down. Then we're supposed to build, or we're supposed to find the unitary transformation that's going to take our reference state, rotate through the Hilbert space, and give us the desired target state over here. But we're not just going to lay down that unitary transformation. Rather, we're going to build it out of a simple set, or a set of simple universal gates. So there'll be a set of gates that do simple operations. In Adam's discussion, he wanted gates that only talk to 2 of the qubits at a time. But we're going to put these Lego blocks or circuit elements together in a particular way to produce the desired transformation. If we are working with these discrete elements, there's a tolerance. We might not get exactly to the desired state, but we'll get very close to it. And we have to decide when we've succeeded. And so we'll introduce this tolerance here so that by some measure we're close to the desired state. And then we build all the possible different circuits, and we find the one that's optimal, or the one that counts or includes the minimum number of gates. And that then, that simple counting of the number of gates is what we call the complexity. Now, as Adam noted, and a theme that will reoccur in my talk, is that I made a number of different choices in describing how I'm going to compute the complexity. And a question is, does the answer I get for the complexity depend on these choices? And the answer is, of course, yes, it does. It has to. That's obvious. And so this is a new kind of a beast, and so we're going to have to get used to it, to learn its properties. But in general, we're not going to do this computation once. What we'd like to do is we'd like to do this computation for a whole family of target states. You know, I may choose my favorite model of calculating the complexity. My postdocs may choose another. Your grad students may choose another. And we'll each get a set of numbers. And then the question will be, is there some kind of interesting physics that those numbers are informing us about? But the question at hand is, how do I apply these ideas to a quantum field theory? And so I'm going to start with a very simple quantum field theory, namely I'm going to start with a free scalar field theory. So here's the Hamiltonian. One of the things that we've learned is that to make sense of the complexity, we have to introduce a regulator. And so I'm going to regulate that theory by putting it on a lattice. But in doing so, I've really converted the problem now from my quantum field theory to an infinite family of coupled harmonic oscillators. So that's starting to sound like a doable problem. But that infinity is still somewhat annoying. And so I'm going to simplify the problem even further. I'm going to reduce the problem to a question of studying complexity with two coupled harmonic oscillators. Now, that's a very simple problem. We know what to do when we're faced with this Hamiltonian here with our two coupled masses. What we do is we find the normal modes, and that reduces the problem to two uncoupled harmonic oscillators. And so we can start to solve. We can start to write down the wave functions. Here's the ground state wave function for this particular problem. If I insist, I can rewrite this wave function in terms... Oh, the wrong button. Oh, dear. Oh, there we are. Excellent. So if I insist, which I'm going to, I can rewrite my wave function in terms of the coordinates specifying the positions of my masses in the original problem. And what I get is a Gaussian that's written out like this with the parameters related to the normal mode frequencies. Now, I'm going to pause and say, well, that's a very pretty wave function. Let's pick that wave function as our target state in our warm-up problem here. So we have a target state. The next thing that that I'm going to look for is a reference state. And the reference state I'm going to choose can go by the name factorized Gaussian, but the key idea here is that the two masses, they're both in a Gaussian state, but they're not coupled. They're not entangled at all. And so that's going to be my reference state. I've introduced some new scale, some new frequency, omega naught, and it's not until the very end of the talk that I'm going to specify or discuss choices for that omega naught, but it's a new parameter that enters the game through my reference state. The next question is, well, what are my gates? What are my unitaries that I'm going to use to build my transformation that's going to take me from here to here? This is quantum mechanics, and so the natural operators that come up in our discussion of the oscillators are the positions and the momenta. So we can simply use those then to build unitaries or our gates for this particular problem. So here's a simple gate. It's a trivial gate. All it's doing is it's multiplying the wave function by a phase. And so these zero indices here indicate that these aren't either of these operators up here. Rather, these are just C numbers. And so they're placeholders, and I'm going to use them in the white space when I fill out some more gates down here. But the key in this gate is there's an epsilon there, and that epsilon is a small parameter, and what it's ensuring it's going to appear in all the gates is that each of the gates makes a very small change to the state once it acts. And so I'm only going to get a finite transformation then by acting with a whole string of these gates in a row, as we'll see. So that's a trivial gate. Some more interesting ones that might be familiar is if I stick a p or an x up in the exponent there, those are then the translation operators. This first gate with pi is shifting the xi by some c number amount, some small epsilon times my c number, x naught. In this case, with the xi up there, what I'm doing is I'm shifting the momenta, or since I'm working with a wave functions in a position space representation, that just means I'm multiplying by some small plane wave component. Things get more interesting when I introduce two operators in the exponent. So there are two classes, one where the two indices don't match. So for example, here I've got a pj, and what that's doing is it's shifting xj by an amount epsilon times another operator xi. And so what this gate is doing is it's entangling the two masses. Similarly, I can have an xi and a pi, both up in the exponent. What that's doing is it's shifting xi by an amount proportional to xi, or it amounts to rescaling that variable. And so I'll call that a scaling gate. Now, I could continue this operation. I could continue to be more creative. I could have x squared, p squared, x cubed, p cubed, more and more operators and more gates from which to implement my circuit or my transformation. But I'm just going to stop here because I know with this collection of gates, I already have enough gates to perform the desired transformation from my reference state to my target state. And this is just a warm-up problem, and so we're going to see how far we can get or how to proceed with this. The idea is that I'm supposed to apply a string of these gates to my reference state, and with an appropriate string, I'll end up with the desired target state. Now here's a simple example where I apply these particular gates. So I apply many Q1s, many Q21s, and then Q2s. Each of them are doing a different step. In that simple example, I can figure out how many times I have to apply each of the gates. And then I count how many gates there are in the circuit that performs that transformation. And in this particular case, I get a result that looks like that. The name I've given that, however, is not the complexity. I've called it the circuit depth. It's the number of gates in my circuit here, but I have no reason to suspect that that is an optimal circuit, i.e. that this is the minimum number of gates. And so this is just a number that characterizes that particular circuit, but it's not yet characterizing the complexity of the problem in the hand. So the question that we face is, how are we going to find the optimal circuit? In principle, what I have to do is I have to put together strings of these operators in every different possible way, try and identify which ones produce the transformation, and then on top of that, find the shortest string, the optimal circuit that gives us then the shortest circuit depth and the complexity associated with this transformation. Well, what I'm going to do following Adam is I'm going to steal some ideas from Mike Nielsen, who in turn stole his ideas from the literature on Hamiltonian control theory. But essentially the first step, well, there are a number of salient ideas. I'm not studying exactly the same problem. He was working with qubits up there. But the first idea is that we should give up on this idea of working with discrete gates. Rather, I should think in terms of smooth functions, working on some smooth space. And so rather than writing the circuit as a string of discrete gates, I'm going to write my circuit in terms of this path-ordered exponential. But you can think of that path-ordered exponential as a continuous version of this string of gates. Wrong one. Sorry. Oh, I'm getting good at that. Let's see. Okay. So there's a path ordering here which runs from right to left. Up in the exponential, we have all of these operators that appeared in the exponentials of the gates. And so we can think of this as a string of gates. And I've introduced a new parameter s, which is sort of labeling, or essentially labeling our position in that particular string as we build up the circuit by applying exponentials of these operators. The epsilon has disappeared, but we've got the differential ds, which is essentially playing the same role as the epsilon in our discrete gates. And I've also introduced these yi's, and you can think of those as being on-off functions that are telling me when in the string I'm turning on a particular gate and turning it off, or turning on the different kinds of gates as we go along. Given this construction, what Mike pointed out is that what's important is not the final transformation, but how we're putting the gates together. And so we should think not just about this entire circuit, but we should think about how we got there. We should think about trajectories moving through the space of circuits, or the space of unitary transformations. And so the circuit starts, or our trajectory starts, with the trivial transformation where we haven't applied any gates, and it's going to end at some special transformation here that realizes the desired transformation. In this particular context, I can also give these on-off functions a different interpretation. In fact, I can think of them as velocities along these trajectories. And there's a very specific way in which you can, well, realize that idea of yi being a velocity. So now I have this problem, or this idea, that I'm moving through some space of unitary circuits or unitary transformations. I've got these velocities yi, and so we can use our classical mechanics intuition, and we can think of this problem as the problem of the motion of a particle through some interesting geometry or through some interesting space. The way that we're going to find the optimal trajectory in physics is that we're going to minimize an action. In the present problem, what I'm doing is I'm minimizing a cost function, namely the number of gates, or essentially this integral over the on-off, or over the velocities along my string of gates. And so the problem at hand is very much like finding geodesics with a somewhat unusual action there. And Mike goes on to discuss that, in fact, what we're describing here are geodesics in something known as Finsler geometry. But I'm going to step back so that I can use more of my physics intuition, and I'm going to change this cost function, and I'm going to write it instead in this form here, where I've got the square root of the velocity squared. And that's now a familiar action, or hopefully a familiar action, from particles moving in some space-time. And so what I'm really doing now is I'm finding a geodesic in an ordinary Riemannian geometry. I won't have time to talk about it today, but you can also, well, Adam was already talking about this in the discussion I've got there, or in the original choice I made there. I was counting each of the gates in the same way. You may choose to count different directions or different kinds of gates in different ways by introducing a more interesting metric here, but I won't touch on that for today's talk. So here's our problem. There's one step that I kind of subtly fell into Mike's discussion of using matrices rather than operators up here. And so one has to understand what the equivalent of this equation is when I'm using these operators. It turns out that's not so hard, but the way Ro and I proceeded was we converted our problem to a matrix problem. The idea being that our initial state, our final state, are both Gaussians. And so rather than thinking about the wave function, we'll just think about the quadratic form that lives up here in the exponentials. So now I can think of our reference state as being characterized by this matrix and the target state being characterized by that matrix. I can translate all of the gates to a matrix language. The generators take a very simple form now. And one of the things that this does is it makes us realize that the problem that we're working with has an underlying symmetry or a GL2 structure in it, in that these generators are the generators of this particular group. Okay, so here's my problem. I said that I'm looking for geodesics in some interesting metric on this group. There's a formula that you may recognize from Adam's talk. I'm going to spare you the details. You grind out. What you find is a metric that looks like this, where the y, the rho, and the tau and the theta are just coordinates which parameterize our position or parameterize our circuits. So we have to find geodesics in this space. Before we find the geodesics, we better talk about the boundary conditions. So we're starting at the origin at 1, and we want to end up with a transformation that produces our target state. I just plug this into here, and what you find is an equation like that. Comparing the two then puts a set of constraints on my endpoints in this particular parameterization of the circuits in terms of the physical variables there. One of the things you may notice here, if we stare at it for a bit, is that tau and theta only appear in their sum, and the difference doesn't appear anywhere. That means that this combination is not fixed. And so it's not a single geodesic that achieves this transformation, but there'll be a whole family of them. But that's not really an issue. We'll just minimize over the family of geodesics and find the shortest one. Looking at those constraints a little bit more, what you see is that, well, these are the boundary conditions for our geodesics. Now then, there's some more calculations, but I'll just draw some pictures. Remember, this is our geometry. Y is sort of sitting here at some linear direction. I've suppressed it in the picture. Rho really is a radius, and theta is an angle, and tau is some other linear direction. We're supposed to find geodesics that start at the origin and then make their way out to this spiral that's given by the combination tau plus theta equals pi. That was one of the boundary conditions at the end. So here are possible geodesics. If this was flat space, it's a little bit more complicated than flat space, but if this was flat space, it's clear what the shortest geodesic is between the origin and the spiral. It's the one that just goes straight across over here along the theta equals pi axis. And so it turns out that even in this more complicated geometry, that is the correct minimal geodesic. There's an associated circuit. No, I was looking out of the corner of my eye. And when I'm ignoring you, then I'll be looking up there. I won't. Oh. Was that me? Oh, maybe. There we go. Okay. We have a simple circuit. We can calculate the complexity. But the clever thing to do is we want to re-express. I'm sure that wasn't me. We want to re-express the answer in terms of the parameters in the problem. And so it has a simple, the complexity has a simple story written in terms of the normal modes. That suggests that we should think about the problem in terms of the normal modes. There's a simple way to transform everything. It's just a rotation from the original positions to the normal mode positions. The reason we do that in the original problem is that my ground state is a factorized Gaussian in the normal mode coordinate system. But my reference state is also still a factorized Gaussian. And so what this circuit is doing, now it's turned off over here. How about you keep that? What that circuit is doing, okay. That time it wasn't me. What that circuit is doing, we have, in the normal mode subspace, we have a factorized Gaussian going to a factorized Gaussian, and so we could imagine wandering around in the space of wave functions, but the minimal circuit does what seems like the simplest thing. It just travels straight across and pumps up those two diagonal elements, and that's all it does. And that's an important lesson when we go to N oscillators. Because the lesson is that in the general case, what this complexity model does is it'll just pump up or live on this normal mode subspace. It won't visit the rest of the geometry. If I look at a warm-up problem for a lattice of oscillators where, no, you just hold on to that, where we just, we've ignored the coupling between, and so it's simply just pumping up the individual oscillators. What I find is that the complexity is very simple. It's just a simple sum, and what comes out is a factor of n to the 1/2. Now, from our holographic studies, though, that may seem problematic in that what this is saying is that n is essentially the volume of our time slice divided by the cutoff to the appropriate power. And so what this model is saying is that I get a result like that with a square root, whereas in the holographic situation, I got an extensive result. Now, that's not saying that there's a right or a wrong answer, but this is a place where we get to make a choice. If we want to make a choice, or one way to proceed, is if we want to get an answer that compares well with holography, is we just simply choose a new cost function. We choose one without a square root, which just does a single sum like that. And what that'll accomplish is that the final result in this problem and in the subsequent problem will just be proportional to n, or it'll give us an extensive result. So now let's look at the full problem of a system of coupled oscillators on some lattice. There's some more interesting dispersion relation, but we know from field theory that those modes are dominated by the UV, and that means that most of these modes, or most of these excitations, have energies or frequencies proportional to the cutoff. As a crude approximation, I'm just going to stick that in there. I'm going to do the sum, and I'm going to get an answer proportional to n. But now I'm going to ask the question, what should I choose for my reference frequency, this omega naught? And there are different choices you can make. It can be in the IR scale, it can be in the UV scale, and depending on the choice I make, I may or may not see this extra logarithm involving the cutoff in my answer. But that's actually very similar to something we saw in holography. So these are the various choices I have for the reference frequency. It's kind of annoying. No one of them seems terribly appealing. But again, there was a similar issue having to do with the normalization of certain terms or certain vectors in the complexity equals action scheme, and we saw exactly the same set of ambiguities. When we wrote this paper, we were left wringing our hands, thinking that there may be a problem with complexity equals action. But what we see is that this simple model reproduces this unusual feature. And so I'm told that I have no time left, but here's some, here's an outlook slide. So with a very simple model, what we have is something that reproduces some features surprisingly well that we didn't understand in holographic complexity, and there are lots of things that one might explore. So at that point, I'll thank you for your attention.
Okay, other questions, please?
I think Edward wants to.
To get something reasonable in quantum field theory, don't we have to restrict to a finite dimensional space of states somehow? If you start doing these things in infinite dimensions, you probably
But
won't
that's
like
what the
it.
regulator did, is that?
Well, the regulator gave us a finite number of modes, a finite number of oscillators, but there's still an infinite number of states. Somehow you need to put in the fact that you know the temperature of the system.
So I guess my answer to that is I don't think so, no. In that I seem to have done away with that when going to the oscillators rather than the qubits.
But you didn't construct arbitrary states.
Not yet, no. But well, okay, yeah, not yet.
So before you went to the Nielsen's approach and you considered the unitary gates, you had a sort of various things like stretching the X or stretching P and so forth that didn't seem to be well tailored to sort of the ADS-CFT context with bulk locality. You might have thought you would want some Wigner-like, composite thing. So my question is, when you did switch to the Nielsen's approach and you expressed the optimal path by this geodesic in this
Right.
Finsler space, if you work backwards to sort of try to say what would be the closest unitary gate, would you see something that is more tailored to sort of bulk locality? Like instead of shifting P or shifting X, would you see some sort of combination of that?
I'm not sure where the question is coming from, but I think what you're saying
It's a question
is,
about what is the unitary gate? What is an optimal set of unitary gates you would like to employ?
right, but I don't know what your intuition is, so I'm going to give you an intuition, which was that you were thinking along the lines of perhaps a mirror network where you insert, I mean, what I did is I pumped up the different modes all at the same time. You know, I just worked on all of them simultaneously in parallel, whereas what the mirror network suggests that one should be doing is working first at long wavelengths and then work our way down to the UV. And so there's an ordering in the circuit. And so what you may be asking is not about the gates, but about the details of the metric. Certainly the metric that I was using in this simple example wasn't producing that kind of behavior, but with a more interesting metric where perhaps I introduce these penalty factors that I didn't get to talk about, then you could get this kind of ordering between different wavelengths or different frequencies. So I answered a question. I'm not sure if I answered your question.
Maybe following up on the previous question, wouldn't it be much simpler to try this first for a free fermion, because you have finite dimensional Hilbert space, and
You can do that.
use the
equally
creation
well,
annihilation in Fock space?
No, you could do that as well. Sure. This is where
Simpler, yes, yeah.
this is where we started. We thought this was the simplest.
If I understood correctly, locality of the gate become locality in phase space?
Sorry, say again?
Locality of a single gate become locality in phase space?
Locality of a single gate become. I don't really see that in the discussion, but I mean, well, okay, I'll just leave it at that. I mean, yeah, no, I'd be answering another question. Go ahead. Okay, sure. Yeah.
Let's thank Rob again and all the speakers of the day.